Hello, and welcome to a new edition of H.E.L Explains with your host, Dr. Mario Toubes-Rodrigo. And today we're going to be singing about the unsung hero in calorimetry, the phi-factor. If you recall, a couple of videos ago, I mentioned about coffee cup calorimetry, in which we use just a mug of coffee to give some examples about calorimetry. In that case, it was a diabatic calorimetry. So today we're going to carry on with the same kind of analogy. However, in our case, our coffee cup is not going to be polystyrene, it's not going to be insulating, it's going to be just a normal coffee cup. So yeah, we have our cup of coffee full of this energizing brew that is going to power us through the day, and we have it in our desk as we are working. However, we know for a fact that the coffee is not going to maintain the temperature over time. It's going to become cooler because of the exchange of heat between the coffee and the environment. And this heat exchange is going to occur where the environment and the coffee is going to be in contact. So it's going to happen around the surface of our coffee cup. That's where the heat is going to be exchanged. So if the heat is going to be exchanged on the surface of the coffee cup, this means that the geometry of the cup is going to be very important in this process. So let's just imagine that our coffee cup is going to be a cylinder. We know that the volume of the cylinder is going to be pi times the radius squared times the height of the cylinder. And the area, on the other hand, is going to be 2 times pi times the radius times the height plus 2 times pi plus radius squared. So if we have, for example, different cylinders that are going to have the same height, but the radius is going to change, we can see how the volume is going to change so much faster with the increase of radius than the area. This is going to have a huge impact on how the heat is going to be exchanged. So let's see how. The bigger our mug is going to be, the slower it's going to cool down. So for example, if we have our coffee as espresso, cooling down by 1 centigrade is not going to take more than 15 seconds. However, if we have our coffee on a 1 liter cafetiere, this time is going to increase. I'm going to be talking about 2 minutes to try to cool down by 1 centigrade. However, if we carry on scaling up and we have industrial size kind of reactors, just to cool the same temperature, so just 1 degree Celsius, is going to take up to 233 minutes if we are talking about 25 cubic meters of coffee. But yeah, Mario, we were talking about the phi-factor. So how does this have to be with the phi-factor? Well, the phi-factor is a constant that is described as the percentage of energy that we have to use to heat up or to cool down the reactor, the vessel in which our liquid is going to be. And it is determined by the equation phi equals 1 plus the mass of the vessel times the specific heat of the vessel divided by the mass of our reagents times the specific heat of those reagents. So if we are talking about very big masses, what we're going to have then is that the reactor itself, the mass is going to be negligible compared to what the mass of our reactor is going to be. So in high reactors, then the phi-factor is going to be very similar to 1. So if we want to test for calorimetry using a calorimeter, then we will have to think about how the phi-factor, how the heat that we are going to be using to heat up our vessel is going to impact the readings that we have. So why do we care about phi-factor? Well, phi-factor is going to have a huge impact when we are trying to determine constants and variables in our chemical processes. So for example, it's going to affect thermodynamic values such as the enthalpy and the equilibrium constants. It's going to affect kinetics such as the reaction rates and the characterization of material properties, phase transitions, melting points, specific heat capabilities. However, where the phi-factor really shines through is when we are trying to design safer processes. I mentioned it before. When we have industrial processes and we have these huge reactors, the mass of the reactor itself is going to be negligible compared to the mass of the reagents that we have inside, and therefore the phi-factor is going to be approximately 1. But when we have small-scale experiments, like the ones that we have on a bench scale, then the phi-factor is going to be much higher because a lot of the energy is going to be used to heat up the container where the reaction is happening. So in order for us to understand what the real risks of this kind of reaction have, we need to actually characterize this phi-factor to use it as a correction factor and therefore accurately predict what is going to happen in a larger scale. You know that I really like my take-home messages, and I think that for me the take-home messages from this video are, first of all, that phi-factor is a fundamental value, and it is determined as 1 plus the mass of our vessel times the specific heat of our reactor divided by the mass of the reagents times the specific heat of those reagents. Secondly, when we have huge reactors, this value is going to be very similar to 1. But when we are characterizing these reactions that are going to happen at large scale, then this value is going to divert. So this is going to bring us to my third and last idea that I want you to bear in mind. We really need to characterize this phi-factor. We really need to know this value in order to correct the values of our experiment and therefore predict accurately what is going to happen in our reactor. So that is all from me. Thank you very much for your attention, and if you have any questions, if you have any comments, just come back to us. My name is Dr. Mario Toubes-Rodrigo and I am the Applications Leader at H.E.L. Thank you.